Most people think they already know where they come from, and that confidence is exactly the problem. Pick up the nearest metal object, something like a coin or a key or a zipper, and consider this. The iron and copper and zinc in that object were manufactured inside a star that exploded before our sun existed. That is not a poetic statement, it is nuclear physics. And yet almost everyone treats the question of origins as if it were about geography or genealogy or, at most, human evolution out of Africa. All of that accounts for the last few 100,000 years of a story that stretches back 13.8 billion years, which means most people quit asking right before the answer gets interesting. You have heard the phrase, "we are stardust," because it shows up on t-shirts and in folk songs and at graduation speeches, and it has become so familiar that nobody stops to ask what it actually means. What nobody tells you is how terrifyingly specific the claim really is. When an astrophysicist says you are stardust, that person is making a precise element by element, atom by atom assertion about the origin of the matter that makes up your body. And the detective work behind that assertion might be the most stunning proof humanity has ever assembled. Hold up your hand and look at it. You have skin and muscle and bone and blood, with iron running through that blood, calcium packed into those bones, and carbon forming the backbone of every organic molecule your body contains. The question is where those specific atoms were before they were in you, not metaphorically, but literally. Carbon came from food you ate, which came from a plant or an animal, which pulled it from soil or air or water. But keep going past the soil, past the atmosphere, past the oceans, past the formation of Earth itself, and you end up asking a question that takes you inside exploding stars. That is not said with a wink. The iron in your hemoglobin was forged in the core of a massive star during the final day of that star's life, in the hours just before it tore itself apart. And that sentence is as literal as anything in astrophysics. For most of human history, people assumed the Earth was built from completely different material than the heavens, and Aristotle made that assumption official. Terrestrial matter, he taught, is composed of earth, water, air, and fire, while celestial matter is a fifth essence, a quintessence, perfect and unchanging and having nothing to do with what exists down here. That framework persisted for 2,000 years, which is a staggering amount of time to believe you are made of different stuff than the stars. What broke that belief open was an optician in Germany named Joseph von Fraunhofer, who in the early 1800s pointed a spectroscope at the sun and noticed dark lines crossing the spectrum of sunlight where specific wavelengths had gone missing. Over the following decades, scientists realized those dark lines correspond to specific chemical elements because each element absorbs light at signature wavelengths the way a person leaves a unique fingerprint. When they compared the sun's spectral lines to hydrogen, sodium, iron, and calcium here on Earth, every single one matched, which meant the sun was made of the same material as our planet. The full picture took another century to come together. A young astronomer named Cecilia Payne analyzed stellar spectra for her 1,925 doctoral thesis at Harvard and reached a stunning conclusion. The sun is overwhelmingly composed of hydrogen and helium, far more than anyone had assumed. Her thesis advisor, Henry Norris Russell, told her she had to be wrong and convinced her to soften the finding. And then 4 years later, Russell arrived at the same conclusion himself. Payne had been right all along, and her work connected the chemistry of the heavens to the chemistry of everything else. What that means, taken together, is that over roughly 100 years, humanity went from believing the cosmos was made of unknowable quintessence to proving that the same elements in your kitchen, your bones, and a handful of dirt exist in every star we can observe. The universe does not sit out there in some way that excludes us, because we are in the universe and the universe is in us. And that is meant in the most literal, chemical, atomic sense possible. Knowing that stars share our chemistry only raises a deeper question, which is where that chemistry came from in the first place. And answering it requires going all the way back to the first few minutes after the Big Bang. Temperatures in the first fraction of a second were so extreme that matter as we know it could not exist, leaving nothing but a seething plasma of quarks and gluons and other fundamental particles racing apart. As the universe expanded and cooled, something happened within the first 3 minutes. Protons and neutrons fused together in a process called Big Bang nucleosynthesis, producing hydrogen nuclei, helium nuclei, and a trace of lithium before the temperature dropped below the threshold where nuclear fusion could continue. That deserves a pause. The Big Bang, the single most energetic event in the history of the universe, the event that created all of space and time, only managed to produce 3 elements on the periodic table. Hydrogen, helium, and a whisper of lithium account for the entire chemical output of creation, which means everything else, the carbon in your muscles, the nitrogen in your DNA, the oxygen you are breathing, the iron in your blood, the calcium in your teeth, the phosphorus in your bones, came from a different kind of furnace altogether. And this is where the story turns magnificent. After the Big Bang, the universe was a vast, featureless cloud of hydrogen and helium expanding into darkness. And it stayed that way for an almost incomprehensible stretch of time. For longer than complex life has existed on Earth, no photon traveled to any eye because there were no eyes. And there was nothing to see even if there had been. Astronomers call this period the cosmic dark ages. And for roughly 200 million years, the universe sat in what you might describe as a sensory deprivation chamber, the size of infinity. Gravity, though, is patient. Over those millions of years, slightly denser regions of gas pulled in more gas, and those clouds collapsed under their own weight, growing hotter and denser at their centers until conditions at the core reached 10 million degrees, at which point hydrogen nuclei slammed together fast enough to overcome their electrical repulsion and fused into helium, releasing enormous energy. The first star ignited, and the Dark Ages ended. Those first stars were enormous, 30 to 100 times the mass of our sun, and they burned through their hydrogen at a furious rate. But here is the part that matters. Fusing hydrogen into helium is just the opening act. Once a massive star exhausts its hydrogen, the core contracts, heats up further, and begins fusing helium into carbon through what physicists call the triple alpha process, a sequence where 3 helium nuclei collide in just the right way to form a single carbon nucleus. Every carbon atom that forms the basis of every organic molecule, every protein, every strand of DNA, every living thing that has ever existed on Earth was forged by that process in the belly of a star because there is no other natural source of carbon in the universe. A sufficiently massive star does not stop at carbon either. As the core keeps contracting and heating, carbon fuses into neon, neon into oxygen, oxygen into silicon, and silicon into iron, with the whole structure resembling a set of nested shells like an onion, where each layer fuses a different element at a different temperature. Hydrogen still burns in the outermost shell, while helium burns deeper in than carbon, neon, oxygen, and silicon, with iron accumulating at the very center like ash. Each successive stage requires higher temperatures and proceeds faster than the one before it. So a star might spend 10 million years fusing hydrogen, 1 million years on helium, a few thousand on carbon, and then fuse silicon into iron in a single day, roughly 24 hours, after millions of years of steady burning. And then everything stops, because iron is the end of the line. Every element lighter than iron releases energy when fused. And that energy is what holds the star up against its own crushing gravity. But iron sits at the bottom of the nuclear binding energy curve, meaning fusion past iron, absorbs energy instead of releasing it. The moment a massive star develops an iron core, it has built its own death sentence, because the furnace has gone cold and the core can no longer generate the outward pressure needed to support the weight bearing down on it. What happens next takes about 1 second. The iron core collapses at nearly a quarter the speed of light, compressing so violently that protons and electrons merge into neutrons until the entire core becomes a ball of neutrons roughly 12 miles across, denser than an atomic nucleus. The outer layers of the star, still plummeting inward, slam into that incompressible neutron core and bounce, sending a shockwave ripping outward that tears the star apart in what is called a core collapse supernova, classified as type 2. During that detonation, one star briefly outshines the entire galaxy it lives in, burning brighter than 100 billion stars combined for a few weeks. The Crab Nebula, that glowing remnant visible through a decent backyard telescope, is what remains of exactly this kind of explosion, one that Chinese and Japanese astronomers recorded in 1054 AD. Two things happened during that explosion that matter for this story. First, all the elements the star manufactured, the carbon, oxygen, silicon, and iron, get blasted across interstellar space, like fertilizer scattered across a field. Second, the explosion itself is so energetic that it drives nuclear reactions, creating elements heavier than iron, things like gold, platinum, uranium, and iodine. Every heavy element on the periodic table is forged in extreme violence, either in the cataclysm of a supernova or, as scientists confirmed in August of 2017, in the collision of neutron stars. That confirmation came when LIGO detected gravitational waves from two neutron stars spiraling into each other, an event cataloged as GW170817, and telescopes around the world watched the aftermath glow with the spectral signatures of freshly manufactured heavy elements, gold and platinum, assembled in real time and observed by human instruments. That was not a theoretical prediction being confirmed decades later. It was cosmic alchemy happening live. Here is a fact that should restructure anyone's relationship with jewelry. Every gold atom on Earth was produced in either the death of a massive star or a collision so violent it warped the fabric of space-time, because the universe offers no gentle method for manufacturing gold. The uranium that powers nuclear reactors and has shaped geopolitics for 80 years was synthesized in a cosmic explosion billions of years ago. And these are not poetic comparisons, but the origin story as written in spectral lines, isotopic ratios, and the nuclear physics replicated in particle accelerators on Earth. The full proof came together in a landmark 1957 paper, authored by Margaret Burbidge, Jeffrey Burbidge, William Fowler, and Fred Hoyle, known to every astrophysicist simply as B squared FH. That paper mapped out, element by element, which nuclear reactions inside stars produce which entries on the periodic table. And William Fowler received the Nobel Prize in Physics in 1983 for the work. Before B squared FH, scientists had pieces of the puzzle scattered across different fields. Afterward, they had the recipe book. Dmitry Mendeleev organized the elements by their chemical properties when he published the periodic table in 1869. And what B squared FH did was explain where those elements actually come from, turning the periodic table from a chart into a map of cosmic violence where each square represents a different kind of stellar catastrophe. That supernova debris scatters enriched gas into the galaxy, where it mixes with existing clouds of hydrogen and helium drifting through interstellar space. And then millions of years later, gravity begins the process again. A new cloud collapses. But this time, it is not just hydrogen and helium anymore. It is laced with carbon, oxygen, nitrogen, silicon, iron, and every other element forged by the previous generation of stars. A new star forms at the center, with a disk of gas and dust swirling into orbit around it, and within that disk, the heavier elements clump together because hydrogen and helium are too light to condense into solids at those temperatures. Heavy elements form grains of dust. Those grains collide and stick. The clumps grow into pebbles, then boulders, then planetesimals, then protoplanets, and eventually full rocky worlds. Our solar system formed this way about 4.6 billion years ago. And the sun is not a first generation star, but at least a third generation one, assembled from a cloud enriched by explosions of multiple stars that lived and died before it. Mercury, Venus, Earth, and Mars are all built from the debris of dead stars, making the Earth, in the most literal sense available, a ball of stardust. The evidence for this does not rest on theory alone. When scientists examine the spectrum of sunlight, over 60 elements show up with hydrogen and helium dominating as always, but carbon, nitrogen, oxygen, magnesium, silicon, and iron, all present in exactly the proportions predicted by models of stellar nucleosynthesis and supernova enrichment. The sun's spectral fingerprint works like a receipt, documenting what previous generations of stars deposited into the gas cloud from which our solar system condensed. Scientists can run the same analysis on meteorites, fragments of the original solar nebula that never got incorporated into a planet, and the results are stunning. When researchers cracked open the Murchison meteorite that fell in Victoria, Australia, in 1969, they found over 90 different amino acids, many of them not used by life on Earth. The Allende meteorite, which fell in Mexico the same year, contained calcium aluminum inclusions dated to 4.567 billion years, the oldest solid material ever measured in our solar system. These rocks function as time capsules whose isotopic ratios preserve the precise mixture of elements that existed in this corner of the galaxy before our world formed, and those ratios match beautifully and precisely what models predict for a gas cloud enriched by supernovae. Which brings it back to you, because you are walking, talking stardust. The hydrogen in your body, present in every water molecule and every organic compound, is original material from the Big Bang itself, nearly 14 billion years old, making the most ancient atoms in your body as old as the universe. Carbon, nitrogen, and oxygen, making up the bulk of you, were forged in stellar cores through the triple alpha process and its successors. The iron shuttling oxygen through your bloodstream right now was produced during the final day of a massive star's life in those last hours of silicon fusion, just before the star tore itself apart. Even the trace amounts of gold in your body, roughly 0.2 milligrams, were likely produced when two neutron stars spiral together at a significant fraction of the speed of light. What all of this means is that you are made of material cycled through multiple stars across multiple generations, each one living and dying and enriching the galaxy with heavy elements over billions of years. That is what the phrase "we come from the stars" actually refers to. Not a spiritual statement, not New Age philosophy, but a scientific fact confirmed by spectroscopy, nuclear physics, cosmochemistry, and stellar evolution theory, cross-checked against the standard model of particle physics. When you look up at the night sky, you are not looking at something separate from yourself, but at your own origin, because those points of light are nuclear furnaces doing exactly what previous furnaces did to build the atoms that became you. The night sky is not a backdrop. It is the factory floor. Most people talk about life on Earth as if it happened to the planet, as if Earth sat there inertly and life showed up uninvited. But that gets the story exactly backward. Earth did not just provide a home for life. It provided the raw materials. And those materials were themselves products of cosmic processes, stretching back to the beginning of time, which means Life on Earth is the universe expressing itself in biological form. There is even a kind of economics to it, and that is meant almost literally. Different elements have different cosmic manufacturers. Hydrogen was made in the first 3 minutes and is the cheapest commodity in the universe, available everywhere. Carbon and oxygen are manufactured in the cores of ordinary massive stars, produced in relative bulk. Iron is assembled only in the final hours of the most massive stars, then scattered by their explosions, making it rarer and harder won. Gold and platinum require neutron star mergers, or the most extreme supernovae, the rarest manufacturing process the cosmos has to offer. The reason gold is precious on Earth is not arbitrary. It tracks, roughly, to how difficult the universe finds it to produce, which turns the periodic table into a price list written in stellar death. Feeling small when contemplating the vastness of space is a natural response, given that we are one species on one planet orbiting one star among hundreds of billions in one galaxy among trillions. But the other side of that coin matters more. The atoms in your body trace back to the crucibles of stars that, in their dying moments, scattered those elements across the galaxy, and those elements found their way into gas clouds that collapsed to form our solar system, our planet, and eventually us. We are not simply in the universe, we are of it. The most astounding fact for me is this connectivity. Knowing that the same laws of physics operating at the scale of galaxies also operate at the scale of atoms inside your body. The same nuclear physics powering the sun built the calcium in the bones, holding you upright right now. There is one set of laws, and those laws made everything, including us, which is why looking up at the night sky does not make me feel small. Many people feel small because they are small and the universe is big, but I feel big because my atoms came from those stars, and the evidence keeps accumulating. When NASA's OSIRIS-REx mission brought back samples from the asteroid Bennu in 2023, scientists found carbon-rich minerals and organic compounds, the same building blocks of life, preserved on a rock drifting through space for billions of years. The James Webb Space Telescope is peering back to within a few hundred million years of the Big Bang and finding galaxies whose stars were already manufacturing heavy elements at astonishing rates. The ingredients for life are not a local accident. They're woven into the fabric of cosmic chemistry, present everywhere we look, and whether life has emerged elsewhere remains unknown, but the raw materials are scattered across the entire observable universe. That is what the question, where do we come from, is really asking, not which country, not which continent, not which branch of the family tree, but what the deep history is of the matter that makes up your existence. The answer connects you to every star that has ever burned, every supernova that has ever detonated, every cloud of gas that has ever collapsed in the darkness between galaxies. We come from the universe, not as visitors and not as tenants, but as expressions of its deepest physical processes. The universe spent 9 billion years building the elements, and then another 4.5 billion years on this planet, arranging them into structures complex enough to look back at the stars and figure out the recipe that is not just where we come from, that is what we are.